Hi, everyone. I'd like to welcome Nate Lawson, giving today's talk on when crypto attacks. Nate is the founder of Root Labs and is one of the co-inventors of the Blu-ray content protection systems. And really looking forward to this talk. He's been a help with some of our open source releases of our Keyzar library, which some of you may know is Keymaster internally. And without further ado, I'd like to turn it over to Nate.
Thank you. Thanks, Steve. So yeah, just a little bit more about my background. I've been working with crypto systems for a while, which is why I'm here to talk to you. My day job is that I design and analyze various systems. Most of them are based on cryptography in some form or another. So my focus is really embedded in kernel security and particularly software protection, DRM, crypto protocols. So for instance, this picture here is a fast track transponder that you may be familiar with from commuting. So I took one of those apart last year and gave a talk on security flaws in the fast track system. And that was just a side work for me. Before that, I was at a company called Cryptography Research up in San Francisco. And we worked on also the same kind of thing, designing and analyzing products that really depend on crypto. And what was interesting about the markets for those products is we worked on things like satellite TV systems, where you have really active attackers who are being paid a lot of money to break systems. And so it's a very interesting adversarial model there. And that's where I worked on the Blu-ray disc protection layer. Before that, I reviewed crypto products for a company called InfoGuard Labs, which was related to the NIST FIPS 140 program. So that's where the government basically has to review the products and make sure that the crypto is secure before they're willing to buy large quantities of software or hardware. And before that, I worked in intrusion detection. So what we're talking about today, though, is why crypto? Why would we fear crypto attacks? It seems like a really well understood problem, right? I mean, you block ciphers, you put plain text in, you use a key, you get the ciphertext out. It's really simple. The inverse also works. Public key, you have this sort of analogy of you have a mailbox where you drop a package into the mailbox and only someone with the key can unlock the mailbox and get the package out again. So these models are simple conceptually, and so crypto seems simple. There's books like Applied Cryptography that make it really easy to understand, and it also is very appealing because you have things like proofs of security using things like the random oracle model, where you're looking at a cipher and you're saying if these constraints hold, then the cipher is completely secure, and so crypto sounds really good. And along the way, people got a few lessons with crypto. So early on, back in the early 90s, I don't know if anyone here used PGP. So, no? Okay. Oh, one person. Okay. A couple. Okay, so anyways, back in the early 90s, PGP actually had its own custom cipher. I can't remember even the name of it, something fish. That was just a bunch of stuff that Phil had thrown in there. And of course, it got cryptanalyzed. And so people got the message that, hey, inventing your own block cipher is not a good idea. No one invents their own block ciphers these days, I hope. And people got an additional lesson that, hey, it's probably good not to implement your own ciphers. There's a lot you can screw up in writing your own AES or triple DES. A lot of testing you need to do to make sure you got the implementation correct. So just use the libraries, right? All your operating systems come with it. You've got, in OpenSSL, you have lots of free libraries. In Java, you have things built in. And so people sort of moved on from looking at crypto as a difficult problem and said, well, we just need to sit down and argue about what the key length we should use. Do we use 128-bit or 256-bit keys? And if it was that simple, I wouldn't be here today. So crypto is actually very dangerous. And I hope this talk will give you some idea of how very little small problems with crypto, implementations, protocol design, things like that, can cause your systems to be totally, utterly compromised. So crypto is strong, but it's fragile. I think of it like carbon fiber. I don't know if anyone's familiar with that, but carbon fiber is a very strong composite. But if you bend it the wrong way, it snaps. And crypto is a lot like that. The other thing about crypto is it requires review that's about 2 to 10 times the development cost, both in terms of time and resources. And it's very difficult to build your own crypto systems and be sure you got it right. It can't be secured by testing, unlike other kinds of software, where you can just throw random data at it and see what happens and say, okay, well, it mostly works. You can't do that with crypto. You can have a system that works perfectly well, that takes any inputs and any outputs and seems to work correctly, and someone can basically compromise it to get your private key. And When crypto fails, it usually is a terrible catastrophic failure. You get to change out your root private keys. And I don't know if anyone's gone through that, but it's not a fun experience. So what can you do about this? Well, the first lesson is just don't implement your own crypto. The cost is too great and there's too much of a chance of failure. So instead what you can do is, if you're doing something with data in flight, use SSL or SSH. These are well understood protocols. And for encrypting data that's going to be stored somewhere, use PGP. Makes sense. These have been around for a while. They've been well reviewed. If you can't seem to make your design fit a model of data in transport, data rest, then try reworking it a little bit. If you still feel like you need to implement your own crypto, at least use a high-level crypto library. And what I'll talk about the difference between a low-level library and a high-level library in the future. But a good example is Peter Gutmann's cryptlib, which has sort of a mixed license, and GPG-ME, which is an interface to GPG, and Keyzar, which is an open source Google project. So all of these work with crypto at a really high level. For instance, you ask it for a key and it provides you a key back. And that's not just a binary blob, but it actually has identifiers with it. So you can't use an AES key with an RSA primitive, or even beyond that, you can't encrypt a message without also integrity protecting it. And these kinds of things are important. I'll talk about why. So don't use the OpenSSL or Crypto API on Microsoft products or JCE or these things directly. They're too low level. I mean, you wouldn't write your web server in assembly. You're working at a much higher level. There's no reason to expose yourself to that kind of risk. So I've talked a little bit about what you can do to avoid using crypto. But if you are in a situation where you're reviewing some crypto that already exists, here are some simple things to watch out for. So an obvious confusion in the documentation or in the source code comments, people will talk about like, I'm decrypting a signature in order to verify it. And that's really a confusion of terms. Even though in systems like RSA, does anyone here know what RSA is? The algorithm? Okay, great. Lots of people. That's awesome. So in RSA, it seems like the primitive for signing is the same thing as decrypting or encrypting with a private key, saying things like that. But signing is actually a much different process than encryption in RSA. I'll talk a little bit about that as well. People will use the same names or redundant names for the same operation or data field in a protocol. So that's a sign that people aren't really meshing with their understanding of how a protocol works. A lot of times when you have cross-site development, for instance. People will be overly focused on weird features like salts as the main feature of their product, and the words rainbow tables, which seem to recur time and time again. So also you'll often see things like arguments about why this is right, why what I'm doing it's not standard, but it's okay, it's really strong. Here's why, because I use a really big key, so no one can guess the key. Attackers don't really know what we're doing in here. Or some blog post, hey, this blog post said do it this way, so I'm doing it. And that actually happens more frequently than you'd think. There was this Jeff Atwood article on coding horror. I'm sure some people here read that, where he's talking about he found some crypto flaw in his product where he was using ECB when he thought he was using CBC, and he had this whole post about how it's better to use CBC than ECB. And so someone posted a comment to that, and they said, well, actually ECB does have valid uses, whole disk encryption. And then an hour later, scratch that. Actually, for whole disk encryption, you should be counter mode instead of ECB. And even that is actually not quite correct. So don't depend on blogs for your sources of crypto information. Other warning signs. People will build a long message that has multiple blocks and try to use RSA to encrypt multiple blocks. It's generally not a good way to use RSA. People will insist that in their particular scheme, the IV for a block cipher needs to be kept secret. Usually that's a sign that the system's poorly designed. Spec diagrams from Wikipedia, always a good one. Anyone can figure out what this is actually specifying here, I'll give them $1. I've never seen some of these symbols before, actually. So I think they took it down, actually, after I mentioned this before. So JavaScript crypto. That's another thing, actually, that's a little bit of a warning sign. There's not really any reason to do JavaScript crypto. I mean, I have a lot of people come up to me and argue that, oh, I really need to encrypt something on the browser side, and I really have to do this for performance reasons or whatever it is. But you need to follow down the root of trust in the system. So if you look at it, where did the browser get your JavaScript code from? Well, from a web server, right? Which web server? Well, hopefully we use SSL so we can verify the certificate, We can be sure that the JavaScript wasn't tampered with while it was being downloaded to the web browser. But what keys is that JavaScript going to use? Well, it's being supplied by the web server. So who are you actually trusting here? You're trusting the web server. Your web server supports SSL. It's already been implemented. Rather than rolling your own crypto with JavaScript and not really changing anything here in terms of root of trust and what you're depending on, just use SSL and don't try to roll your own JavaScript crypto. So I want to talk more about other failures. I don't know if I've convinced everyone that it's a good idea or not to implement your own crypto. So I'm going to talk about various attacks, and hopefully we'll see what ways systems can fail. So the first category is system-wide flaws. So these are things that happen sort of regardless of what cipher you chose or what how your protocol works. So this is actually a real example. I hope no one here finds it familiar, but this is from a real company. So they decided, hey, we've got an old cookie scheme, and we just realized it's insecure. We were using CBC mode to encrypt a cookie, but we weren't doing anything to add integrity protection to it. So we're trusting in the fact that because it's encrypted, the client can't do anything useful with this before sending it back to us. And does everyone here know what CBC mode is? Or have an idea? Okay, good. Some hands shaking. Yeah. Okay. Yeah. So CBC mode is okay for encryption, but it doesn't provide integrity protection. So an attacker can actually modify things intelligently in your plain text, just given the ciphertext. And so what they'd said was, well, let's add integrity protection to the cookie. So this is good. They're making a change. They're improving their security. So they used HMAC, which is a reasonable cipher for that, reasonable hash function construction. And so great. So someone said, all right, what do we do now? We've got all these cookies out there with the old scheme, and we've got this new scheme, which is better. So let's upgrade these cookies in the field. Rather than forcing people to log out or whatever, we'll just transparently replace these cookies. So how would this work? Well, they take the client cookie, and they say, oh, is this an old format cookie? Yes. Great. Let's decrypt the data. Check the length. That's fine. OK, we see the version that's an old cookie. Now let's take the contents of the cookie, encrypt it and integrity protect it with HMAC, and send it back to them, and to replace the other cookie. And this is great, right? Anyone see a problem here? Yeah, exactly. You can either reuse old cookies continually, or even maybe create your own old cookie and always send it to the server, even though it's not issuing old ones anymore. All right, that's the system type flaw. Another one is your pseudorandom number generator. So your source of randomness, your PRNG construction. So either doing a bad job with this or poorly seeding it. So unfortunately, in a lot of languages, high-level languages, the default PRNG is not a good choice. So if you look at Python's default random, Java's default random, .NET's default random, all of these languages provide a random number generator, pseudorandom number generator class that is not cryptographically secure. So you have to actually specify that, hey, I want to use the secure version of this, not the one that's used for simulation or whatever. And a cryptographic random number generator has to have particular properties that don't matter if you're running Monte Carlo simulations or whatever. So like, for instance, you need to constantly reseed your PRNG as you get new entropy, because as you're providing random numbers from your pool, you're exhausting the entropy in the pool over time. And that's not necessary for simulation. You don't care about that. You just care about having a long period. And also, you want to make sure it's impossible to guess or perturb the internal state. So let's say you have a PRNG where you're reading in timestamps from files on the file system. Firefox does this. And if you had a poor PRNG construction, an attacker could actually create timestamps on files specifically to exploit the contents of that PRNG pool at a particular point in time. So you're allowing someone outside to control the state of that. And if they could, for instance, force it to 0 or to some constant number, then your keys are totally insecure, even though the attacker can't see those keys directly. So you need to use a good cryptographic PRNG when using it with cryptography. Also, there's a case of cold boot, where if your server just rebooted and you're starting to get requests immediately, SSL requests or whatever, signing requests, your server's only been up a few seconds. Do you have enough entropy to really create a 4096-bit private key that soon? And if not, where are you getting your entropy from? Is it possible that you're replaying IVs somewhere or challenge values? And then a higher level question, who here is actually responsible for this case? Is it the server admin? Is it the programmer? Is it the library author? Is it the person who selected the library? So identifying and knowing sort of who is actually taking responsibility for all these things is important. Another thing that happens at a system level, independent of your particular cipher construction or protocol you're using, is something called sidechannel attacks. And sidechannel attacks have to do with the fact that no one gets to run crypto on a theoretical machine. You see all these research papers, and it'll say, given that the attacker has this and that and can see 2 bits of this or 3 bits of that, then this is provably secure. But crypto doesn't really work that way. So when you run crypto, it has to run on a CPU somewhere, on your server farm, on your desktop, on your PDA, or your cell phone. Runs one of these places. You can have hardware implementations of crypto, but just like a CPU, those are running in a particular location. So this is not a true black box. In fact, an attacker has some level of measurability. For instance, they could possibly submit queries to your server and see how long it takes to get a response back. So there's measurability. There's a lot of shared state on systems, even if you're running with remote users, where you've got, like, let's say you have different SSL keys for different sessions. But the crypto that uses those SSL keys runs in processes on a Unix or Windows box. And that crypto creates little traces of its behavior in form of CPU caches, whether something's on disk or in memory, branch prediction buffer, and even like remnants of data on the stack. So all of these traces provide some level of information about what's happening. Now, it may not be enough information to do anything, but there's been a lot of useful research in this area where you take a small bit of information over a long period of time and you're able to reconstruct someone's private key. Additionally, there's another type of sidechannel attack where the attacker has some sort of control or influence over your choices of keys or resource usage on your server. So for instance, if I can open a lot of connections to your SSL server, I can maybe exhaust your poor PRNG seed by just repeatedly establishing new session keys and using your PRNG that way. If someone has the access to be able to start a process, then they have the ability to use the memory of that process. There was an interesting paper at Usenix Security a few years ago where someone talked about intentionally degrading non-cryptographic hash functions. So basically, if you had just a normal hash table for just a database or some other lookup for key value pairs, and if someone knew the particular hashing algorithm you're using, they could create degenerate queries that would cause your hash table to degenerate to a single linked list in a single hash bucket. And so then you have a denial of service attack against that particular implementation. So all these are cases where an attacker has some level of measurability or control over how crypto is actually running on your system. And from that, they can actually attack the crypto. Things like timing attacks. There's actually a paper called Remote Timing Attacks Are Practical, where Dan Bonnet actually and his team compromised an SSL private key just by measuring the variation of a few multiplications on a server over a LAN and then even a WAN. So it required collecting a lot of samples, but they were eventually able to do it. And that attack was fixed in OpenSSL a few years ago. But there's also power analysis attacks. If anyone here is working on Android, for instance, people have the physical device in their hands, and embedded systems are particularly vulnerable because you're giving the device to an attacker, and basically they can measure power consumption while doing cryptographic operations. They can repeatedly trigger the same operations over and over with different data. They can measure electromagnetic radiation, heat, sound, disk access patterns. The sky's the limit. So this is the case where a system-level problem can actually compromise your crypto. Let's talk about encryption now. That's what people think of, I think, most when they think about crypto. So block cipher modes of operation, I've been throwing around these terms. So a lot of people here have heard CBC or ECB mode. ECB mode is where you encrypt data just a block at a time with no relation between the blocks. CBC mode is where you take the previous block ciphertext and XOR it in before you do that encryption. So you chain together the ciphertext blocks. So that's great. If you're familiar with this, you've seen these terms before. Give yourself a hand. But there's a lot of other modes out there that people are using: OFB, CFB, counter mode. These are all stream cipher constructions. So you take a block cipher and you make it act like a stream cipher, where you're just generating key stream and XORing it with the plain text. And because of that, people can just go through flipping bits. If they know the plain text at a particular point, they can flip the bits of that plain text intelligently. There's complete malleability. There's no integrity protection. And it's fatal if you ever reuse a counter or the keystream output. There's some new things like CCM, which are authenticated encryption modes, where it actually provides integrity protection along with encryption. But again, these have some constraints on them. Like if you ever reuse an IV, you basically compromised your system. So even with people who manufacture devices get it wrong. So here's a USB key I looked at. This one had actually a doc that came with it that talked about how good and how secure this USB key was. Yes? Oh, sorry, it's okay. IV is initialization value. So when you're encrypting a message and you're using the same key over and over, using a different IV makes each encryption different while it's still based on the same key. So if you encrypted the same message twice, like hello, hello, the ciphertext would be different if you used a different IV. But if you reuse an IV, the ciphertext would be the same. And so someone could see patterns in your messages. And they can also modify your messages intelligently. So this one said it was TDEA electronic code book TECB mode, which basically boils down to we're using ECB on your USB drive. It's not something to be proud of. Another problem with encryption, often people will reuse counters in counter mode, and that's a big no-no. So you really paid attention to your design. You've got a client that's using a key. You've done a lot to make sure the counter is unique. Maybe you save its state as you use each time. You force a key refresh if the other side gets rebooted, so you're not reusing a counter value. Maybe even persisted it in some kind of database or disk store, so you're sure that once you start up with that key again, you're not going to reuse a counter value. That's great. What about the server side? So if you're using a shared key, two-way communication with the server, session key for instance, you end up with keystream reuse, which is fatal for counter mode if your counters ever overlap. So in this case, one counter is behind the other counter, but they're in the same space, and they're sharing the same key. With keystream reuse in counter mode, basically what's happened is anytime an attacker has seen a single message from you, and then you reuse that keystream later, they can completely decrypt a different message because they know all they need to basically XOR with your ciphertext and get the original plaintext back. So never do that. Integrity protection flaws. So we talked about encryption. Integrity protection is how you make sure that an attacker hasn't modified your ciphertext after you've encrypted it. So a lot of people will build their own hash constructions. Anyone here work with cookies, building your own cookies, stuff like that? Okay, a few people. So what people often do is they'll say, hey, I've got this nice MD5 or SHA-1 here. It's built into my PHP or whatever. And they're saying, I want to be able to send a cookie to the user, and I don't want them to be able to modify it. So I'll basically take a key and concatenate it with the data I'm going to authenticate in the cookie and SHA it, right? You get this nice random-looking hash out. If you change the key or you change the data, it changes significantly. All the bits flip. Great. It's working, right? Ship it. The user doesn't know the key, right? You choose a 128-bit or 256-bit key, and the user doesn't know it. They can't forge these cookies, right? That's wrong. There's actually a length extension attack here, where if you look at how SHA-1 operates under the covers, if you look in this little sidebar, there's some chaining variables that are initialized at the start of SHA-1. And at the end, it basically, after hashing a bunch of data into these chaining variables, the chaining variables are returned to the user. So these kinds of hash functions are subject to a length extension attack, where once you've seen the SHA of some data, you can always append data to it and update that SHA result to match the data that you appended to it. So as you can see here, if in your cookie construction, if an attacker ever got the SHA of some short cookie for whatever reason, they could then append whatever data is, like maybe changing their user ID or something like that, to the cookie and create a valid cookie that would be authenticated as correct by your system. So you should use HMAC as a construction instead of arbitrary hash function constructions. There's other more esoteric attacks if you, for instance, do key appended with data, appended with key again, and SHA that. There's other attacks that can be done on that. It's a little more esoteric, but just use HMAC instead. Here's another standard. Is anyone familiar with the IETF XML standards for SOAP, et cetera? Work with that? Great. So there's a standard called XML DSIG, which allowed you to authenticate your XML, basically make sure it hasn't been changed. And it worked with this thing called HMAC, like I was talking about. HMAC is a decent algorithm where you're using a hash function in a way that an attacker can't create or forge authenticators for your plain text as long as they don't have the key. But there's a lot of problems with how XML DSIG actually specified the HMAC algorithm. So anyone want to take a stab at this one? Here's a valid signature of sorts. You would have the HMAC of the data stored in this XML format. So there's a couple things here. There's actually two problems. So the first one is, well, okay, it says the output length is 160. That's actually in bits, which is good. But what's wrong if I just specified 0 for the length? Well, now I've got a nice shiny HMAC that no one verifies any of the bits of. The implementation goes in and says, how many bits do I verify? 0. Okay, you pass. Not very good. And even if it checked for 0, set to 1, you have to flip a coin. 50-50 chance of getting the HMAC correct. And in 2 tries, you have a 100% chance. So also, there's another thing where it has this algorithm specifier. And what the standard said was, this algorithm specifier is required to be supported, but other algorithms are also optional. So who knows what implementation of the standard out there allows MD2 or MD4 or whatever for the HMAC hash functions which have been broken. So why is this field even here, though? Who was thinking that, hey, we can truncate HMACs. You can do that somewhat safely, and it saves a couple bytes per message. I mean, a couple bytes. We're talking about XML here, right? I mean, if you had a single comment anywhere, you would be already exceeding the amount that you can save in this field. But actually, the field itself doesn't work for its intended purpose, because the tag itself, both the start and the end tag, is 38 bytes. And the most you can safely shave off SHA-1 is about 10 bytes. So you lost 28 bytes, creating a new field that allows you to truncate something to a less secure value, and gave implementers a lot of different ways to interpret this field that you now have to go revise and spend 6 months. They spent 6 months in the IETF notifying all these vendors. I won't name them all, but you can go to the CV webpage and see the vulnerability of all these systems, big names, basically go out there and saying, yep, sorry, we screwed up, we screwed up, we screwed up. There's no reason for doing this. This was a new standard. There was no backwards compatibility with truncated HMACs. No need for this. It adds overhead, and it's another field that people have to validate. But yet it still persists in the standard. It's still there, but now they say, oh, you need to check for the value. Make sure it's not less than 80. So here's another one. This is starting to get a little more complicated. So put your thinking caps on for this. So if you've got CVC encryption with an HMAC, okay, this is better. We're improving systems here, but we're also improving our attacks. So for AES, let's say you're encrypting a message block that's the message is only 14 bytes long. So the block size for AES is 16 bytes, or 128 bits. So you have to put something there. Do you put zeros in there? Do you put some random data? What do you put in the remaining 2 bytes before you encrypt it? Well, with a lot of systems, they have this custom CBC padding, where you put the message length -1 in the bytes. So if your message had 2 remaining bytes, the last 2 bytes would be set to 1. If it had 3 remaining bytes, it would be 2, 2, 2, 3, 3, 3, 3. You get the idea. This gives you a way to validate that you got the correct padding value. But let's say someone implemented the system, and they did a very straightforward thing. So error return values are good, right? Everyone likes to know exactly what went wrong. Did you bug your system? So here's 2 different error values in this data block. So the first one says, padding's incorrect. We decrypted it, but the padding bytes are wrong. We got 555, for instance. That's not a valid CBC padding. Another one is integrity failure. The padding was valid, but someone modified the message. And if your implementation returned these 2 different error messages, then an attacker could actually use this to decrypt your messages. Here's how it works. You take take a block, and it's second to last one usually, and then you set up the block with different guesses for the last byte of the message. You don't know what the last byte is, but you're going to iteratively guess the plain text. And what happens is if you guess it correctly, the result will XOR to a 1, and you'll basically know that you get an integrity failure error. If you got the incorrect guess, of course, you get padding incorrect. And from just this one bit of information, a different error message, you can iteratively go through decrypting the last byte, then the second to last byte, third to last, until you've decrypted the whole message. You can work your way backwards. Really powerful attack, and one that's very subtle. It's just an error code distinguishing attack. Signature flaws. So most of these are public key based, but some of them are just dumb mistakes. So here's one that I hope no one's made. Basically comparing a hash value to the correct hash value. Very simple, right? Everyone could do like a mem compare or whatever. So this one actually was found in the Wii game console. People use this to be able to attack it and load their own games. So what you do, yeah, so you've got RSA here. You're going to basically verify a signature on some firmware update or whatever. You run RSA correctly. You verify the padding data. I'll talk about that a little more later. And return, check if strcomp returns 0. Strncomp, actually. Well, what does this mean? You know how string functions different from memcomp? Yeah? OK. So the attack. Basically, you just create 256 messages, find some byte in the random padding area that you can vary, and just calculate a bunch of SHAs of these things. And once you get zeros in the first byte, you have a message that will pass for your bogus firmware update. So here's a little Python code which will generate it for the magic number is. So if you add the number 26 to the magic number is, you get a 0 in the first byte of the SHA-1. Really bad. OK. Lacking structure in signed data. So we're going from very simple to a little more complicated. So when you sign data, you actually have to know what you're signing. Think of signing as basically you have a root shell on every machine in your entire company. And you're going to type a command and hit enter. You better check twice or 3 times what you're typing before you hit enter. Because that's what a digital signature is saying. You're strongly attesting that I said this information. So Amazon Web Services had a flaw in it. It basically allowed a client to sign a URL. So what they do is they take the URL and they break it on the common parameters, the ampersand delimiter and then key value pairs of equals between them, and then concatenate key 1 with value 1, key 2, value 2, and then HMAC the whole thing, right? So anyone see the problem with this? All right. So what about these 2 URLs? So the first one is good key 1, good value 1, bad key 2, bad value 2. But that's really just a value, all those. And in the second one, they're separated by an ampersand. And these are 2 separate keys and 2 separate values. These both have the same HMAC in their scheme. So you can send the first one, hiding your bad data in some unused field, like a comment field or whatever, and then get the HMAC for that, then take the one with the bad key, send that with the same HMAC, and it will authenticate, because there's no structure here to what it's signing. The delimiters that were there were discarded as they were signing it. Really bad thing to do. You need structure in what you're signing. An even worse thing to do, but a little more complicated, is some people have actually, and I saw this in a microcontroller product, they actually decided they didn't want the overhead of SHA-1. So what they'll do is, normally with signing, you take a SHA-1 of a message, then RSA process it after adding padding, and you get a signature. But what they did was they said, well, we don't want to do the SHA-1 step. Let's just take the data that we want to send. It's smaller than an RSA block. Let's just process that with the private key and send that out as our signature. Well, there's an attack on that. There's a reason why there's padding in RSA. Basically, what you can do is you can just choose some primes as some messages, send each prime in to get signed. So my message is 3, my message is 7, my message is 11. Just send these in. And you get signatures on each one of these. Now, because RSA has the associative property to it, you can actually combine signatures and combine the data, and the result is also a valid signature on that new data. So like, let's say there's a special message 21. Now, I'm using small values, but the message 21 means delete everything on the server. So you really want to make sure you check the signature before you allow message 21 in. But if an attacker can sign message 3 and message 7, which are maybe some innocuous messages, then they can just take the return signature values, multiply them together, take the messages, multiply them together, and send those 2 together. And now they have a valid signature on the message 21, and you get to clean up your server. And this is the same property that allows what's called blinding, which is an interesting property I might have a chance to talk about. So anyone here familiar with like just basic network protocols, padding, be careful in what you what you create, but be lenient in what you accept, that kind of thing. So padding is usually something you just discard. Who here validates every 0-byte padding field in every message you get, or random padding, or whatever? Almost no one. But in crypto, padding is not something you can ignore. So the PKCS1 signing standard actually has a very specific format for padding because of that previous attack I just talked about, as well as other attacks. So what you do is, to sign data, you prepend some constant bytes, a bunch of FFs, 0, 0, 0, 1, and basically, and then at the end, the SHA-1 hash of the data you're signing. And this is because the hash is smaller than your RSA block size. So your RSA is, say, 2048 bits, but your SHA-1's only 160 bits. So you have to fill in that other data with something else. So you generate the signature over this padded data. And to verify it, it seems simple, right? To a normal implementer, it's like, hey, I can do this. It's easy. I first of all process the message by raising it to the public exponent to verify the signature. Then I just throw away all the padding, get the hash value, validate that against the message, right? Seems good. Now the attacker can create forgeries, though, because for that same 2048-bit key and SHA hash, there's another 1,800 bits that can be any value the attacker wants because you throw all those away. You didn't verify those bits. So especially with small public exponents, like 3 or 17 or whatever, I've actually seen this attack in a hardware system where they used random padding for their encryption, and they didn't verify it in any way. So because it was random. And in that case, what we could do was we could basically calculate a bunch of different values for the message we wanted to forge, and by changing those upper 1,800 bits, which are all thrown away, you can create a valid signature for the lower 160 bits of your choice. So you have to verify every bit of padding data in crypto protocols. And how you verify them is also very important. So remember what I talked about before with the error distinguisher? You have to be careful not to return the wrong error or multiple errors while you're verifying every bit of padding. So you're damned if you do, damned if you don't in this kind of system. All right, public key flaws. So we talked before about the mailbox analogy. So let's see where that breaks down. So DSA, the digital signature algorithm, often used in elliptic curve form, it fails if you know the random value k. So basically the way it works, to sign some data in DSA, what you do is you generate the signature R and S. And basically, don't get too lost in the math, but basically you take a random k, you raise it to a base, you raise it using a base, and you take the k inverse and you hash your message, that's important, and your x, which is your secret key. That's the most important part of this, your secret key. But if you know k, you can basically just with some simple algebra refactor this equation in terms of x. And now everything is public. You know h of m, because you know your message, right? So you can calculate the SHA hash of that as good as anyone. That's public. You know the R value because it got sent across, so you can calculate R inverse. You know the K, that's the given here. And S also is sent across the wire. So now you can calculate the server's private key. So just by knowing one random value from the server, over thousands or millions of signatures, all you need is just one, and you can calculate the entire private key directly. Sounds pretty bad, right? Well, it gets worse. There was that bug in Debian's PRNG for OpenSSL. Anyone heard of that advisory? OpenSSL, yes? A couple of people? OK, great. For those who didn't hear about it, basically what happened was someone commented out essentially one line of code that was all the random data that was being fed into their PRNG to seed it. And therefore, the only bit of varying data that went to their PRNG was the current process ID. So there's about 15 bits of entropy going into that. You can easily exhaust 32,000 values really quickly. So this was a bad bug, right? Well, people were out there going, OK, how many OpenSSL certs do we need to reissue, whatever, whatever. The real question they should have been asking is, how many packages have we signed using DSA with a vulnerable system? Because everyone who issued a single package, including old ones that are in the archive, an attacker, once they know that this problem exists, can go out there and they can basically, go out there, look at the signature, look at the software, and basically say, OK, I can calculate directly what the person's private key was. So you have to revoke every private key that was used to sign a package on a vulnerable system, not generate keys. So generate keys is bad enough. Every key that was generated has to be revoked. You also have to revoke any key that was used, even if without your knowledge, to sign something on a vulnerable system. It's a big deal. But it gets worse. So crypto attacks always get worse. So there's an additional very surprising finding it's not really well known. It's somewhat known in the crypto community, but even there it's a little bit less well known. That basically, even if you know only a few bits of K and can get a lot of signatures, you can basically use this to recover the private key. And it's something called the hidden number problem, which is a bunch of number theoretic stuff. But basically, what it devolves to is that you're using a lattice reduction to basically look at all these numbers which are partially known and you're finding little bits about and combine them all together in a giant lattice where you can use little bits of the key in multiple places to recover the entire key. And very, very awesome research by Bonnet and others on that. So the question was, how many is a few bits? So it varies based on how many messages and signatures you can collect. The less bits, the more messages you need. So, but it's theoretically exploitable down to 1 bit. So even if you could predict 1 bit reliably of the K and get a lot of signatures, you could recover a private key. So this question is, can you just take a guess, 0 or 1, and try that? Yeah, but the number of messages is really large. So because if your PRNG is good and if you seeded it well, the chance of you getting a 0 or 1 is 50% approximately for each of those signatures. As long as there's no bias there in that bit, you're okay. But if you know it for certain, for instance, if I know it's 0 and now I know it's 1 and now it's 0, then I can use that information to attack the system. Okay, we'll cover more. We have more Q&A at the end. So here's another thing of confusion of terminology, I'd say. So people talk about, I'm going to encrypt something with my private key, right? Okay, so RSA has public key, and let's say that you've got some device. You've got a cell phone. Your cell phone has an RSA key in its flash. It's a public key, and what it's going to do is it's going to verify that your Android updates came from Google, right? You want to make sure that you have the right firmware that you're going to install on your system. It's not a Trojan or something. So you could take this public key and you can verify the signature. That's all fine. Okay, we're okay so far. Someone comes up with a bright idea. They say, well, we also want to encrypt our updates, and we don't want to have to put another key in there. We just want to use the RSA key we already have. We're going to encrypt the updates as well as verify the signature. That way, people can't find out. We've obfuscated what code we're loading and what the update is. So they said, well, let's keep the public key secret. This doesn't actually work. You can't keep a public key secret. That's the amazing thing about RSA. If anyone can actually see your signature updates, your firmware updates, if they can see just 2 of them and 2 signatures, they can, just using some straightforward algebra, calculate what your public key was. Notice they can't calculate your private key, but they can calculate your public key. So this is an example of using GCD and 2 signatures, how to guess the modulus n. And at that point, you know E and N, and you know the person's public key. So this is an example where conceptually it seems fine. If you have 2 keys and you're not revealing one to an attacker, they shouldn't be able to guess your key, right? But because of the particular properties of RSA, if you can see something about that key, some result of that key being used, you can always calculate the public key. Now the private key, you can't do that. Anyone here heard of SRP? It's a password-based scheme? Good. So SRP is a great protocol, and it's actually a family of protocols that what it does is it gives you password authentication without people being able to do dictionary attacks on the password that goes by on the wire, for instance. And at the end of your negotiation, you end up with a shared key between the server and the client that you can use for encrypting things. So SRP plus SSL is a great combo because instead of having this ad hoc construction where you use SSL to connect to the server, then you type in your password in plain text over standard base 64 encoding and password submission. SRP actually allows you to use the password to derive the session key, and that goes in the SSL. So it's great. It works. You get authentication plus encryption and a user login and all that. This is a description of the protocol. Seems easy, right? I mean, everyone got that? All right. Yeah, so there's a bunch of numbers going back and forth, a bunch of steps where you have to look up or verify various parameters. And like all public key crypto, SRP is very sensitive to what these values are. So here's a particular bug. If you look in step 3 and step 5, what if the attacker just is the client and they send a value a equals 0? This is just some random data that goes to the server. And then you see this little multiplication on the right side. So a gets multiplied by some stuff and equals capital S. Well, capital S is, if you go back to the original thing, is part of how it uses to verify that you're authenticated or not. So the server does this fancy exponentiation twice and multiplication times a with all these private pieces of data and things like that, and gets the value 0. Well, obviously, the client knows that and can predict the result. So there are other bad parameters actually for SRP. There's like about 10 things you need to verify with SRP to be sure that a client or a malicious server, someone impersonating the server, can't screw up your exchange there. And there's actually more attacks. I could go on all day about all this. There's an attack against Tor and IKEs, which is part of IPsec, where this thing called Diffie-Hellman small subgroup confinement, whereas if you let the client choose certain parameters of how you do encryption, they can basically force you to choose one of a small set of signatures, like 0 or 1. There's also things where people have decided, let's use a CRC for integrity protection, just encrypt it and hope people can't modify it. That failed for SSH v1. That's why we use SSH v2 now. Fault injection, where you actually have control over the device and you're sending in voltage spikes or whatever to try to induce false and RSA signatures. And from that, you can extract the private key. So all of these attacks are interesting, and there's a lot more of them. So what do you do about all this? Anyone? Well, as I said at the beginning, there's a lot of good reasons for not doing your own crypto. And if you're working directly with ciphers like AES, PRNGs, unless you're really a crypto system designer and you're willing to spend the 10 times the review time it takes to really be sure you got it right, just don't do it. You know, work at a higher level. Use things that are already there, like SSL, GPG. These are already out there. They're well validated. They're free and available on the systems. Use this as your first resort. And if your design can't fit that, really try to rework it and see, is there any way we can change how we share state or whatever to reuse these capabilities? If you really can't do that, the next best option is use a high-level crypto library, not a low-level one. Use a high-level one where you get primitive, or the interface to it is something that, for instance, you say, take this, encrypt and authenticate this blob, and it basically provides you back a sanity-checked component that you can pass along. So high-level libraries are good. Cryptlib and keys are both pretty good. And if you ever end up using something like this, especially if you end up having to regenerate your own crypto by using low-level crypto primitives, make sure to get a really extensive review of it. I mean, there's a lot of ways. Yeah, cryptographers publish all their stuff because they know that peer review is the best way to be sure that they didn't make any mistakes. But just publishing code open source doesn't guarantee you're going to get that kind of review. So if you have to design your own, make sure you spend the time and resources to really get an extensive review. You have some people here that know about crypto a little bit, and or a lot, and would be great resources for that. So now I'll open up to questions and any comments. Thanks.
If you have questions, I'd like to ask you to line up at the mics so people on the VC can hear them.
If there are no questions, I'll just go on and on about IKE or something.
How do things like the HTTPS null byte bug survive for so long?
Okay, the question is regarding a recent publication at Black Hat of 2 researchers independently found a problem where they can request a certificate on 2 values, one that's malicious and one that's not. And this name that they would request for the certificate would be, one name with a null byte following it, and then another name. And it turned out that the CA, the person who was generating the certificate, would validate one of the fields up to the null byte, and the browser, who is responsible for using the certificate, would validate the other half. And so an attacker can carefully provide both halves, and each party would look at the part that they care about most, which is great for the attacker. This would allow you to get a certificate for Amazon.com or Google.com or whatever, and have it validated by common browsers. How does this persist so long? A couple things. First of all, the people who write the software for the CA are different from the people who write the software for the browser. In fact, each browser sort of has its own different crypto implementation. You have NSS in Firefox, you have Microsoft Crypto API, and Opera and Conqueror and all these others, and Apple has their own as well, Safari. And all of these use different crypto implementations, so it's conceivable that one browser could have been vulnerable to it and made that mistake while all the others were fine. So the problem is that there's a lot of software out there. There's a lot of different people creating different parts of it, and they're not all working together, and you don't have someone, I don't know anyone who's been hired to review both the CA software and a browser crypto engine to make sure that these kinds of mistakes aren't in there. So it's just a lack of overlap between different problem domains. Any other questions?
The attack you were talking about where you would put random things in the padding and eventually work them out because of two different error messages. I understand how you could work out the padding, but once you start going into the message, I don't understand how the logic would be there.
Okay, yeah, that's a good question. It's a little bit difficult to go into all the details of it, so I'll try to give a brief summary. So for the CBC padding attack, where you can distinguish between the two different errors, the property of CBC is that given the particular XOR construction of it, you can actually, if you know bits of the plain text of a block, you can modify the bits of the previous ciphertext block and cause chosen changes in the subsequent block while garbling the previous block. So there's this problem of you can make changes in it, and you can basically garble one entire block while making specific changes which don't result in any garbling to the next block. So if you can get this to line up the right way, for instance, on a padding field that no one verifies, then you can intelligently make changes in a CBC encrypted message without knowing all the details about all the blocks. So this attack actually is not based on that, though. What happens in this attack is that you know what you're trying to produce in the plain text in order for the client to, or the server to accept the result. So in other words, if you have a single byte remaining, so 15 bytes or whatever, you might want the last byte to be a 0. And since the length is external, the attacker can truncate the length to whatever they want. So like, let's say the original length of a message they've seen is that they want to decrypt is 32, two AES blocks. So they could decrease that counter to 31 because it's not protected in any way, and then change the last byte of the subsequent of the second to last block. And as they change this, they don't know what the actual plain text value is, but once they get the value correct, the XOR of two numbers that are identical is 0, right? And 0 XOR some number is that number itself. So once they can get the difference to basically be 1 between these two, or 0 in that case, they've guessed the last byte. And now since they know they can set that byte to be constant, and they can choose that to be whatever they want. So now that they've guessed the last byte, they can change it so it equals 1 in the next round. And they send that message again to the server so that the last byte is now set to 1, and then they keep flipping through the second to last byte until they get that one to be matched to be 1. Then once they get that correct, they know the last 2 bytes, and they can iterate. That attack was found by a guy named Serge Vodnay. So, any other questions?
Oh, well, if there's no more questions, I'd just like to thank Nate again and give him a round of applause.
Thank you.